I'm Dan Milisavljevic. I'm an assistant professor at Purdue University. I've been there for over 3 years. Previous to that, I was a Center for Astrophysics. And previous to that, I did my PhD at Dartmouth College. I'm originally from Canada. That's where I'm born and raised, in Hamilton, Ontario, just outside of Toronto. I went to McMaster University for my undergrad. Um, my slides will go into detail actually about my scientific interests. And I kind of got into this by luck, and I guess by also exploring the questions as deeply as I can in my science. So a lot of snooze is particle physics, and that's not me, but my investigations are trying to understand the progenitor systems and explosion mechanisms of supernovae. In fact, now thanks to multi-messenger astronomy, we have opportunities to explore supernovae using multi-messengers as we hadn't before. Okay? So that'll be the theme. So here's the first slide. This is on behalf of a larger collaboration. A lot of the slides, a lot of the figures from the slides being shown today are coming from a white paper that the snooze group released on the archive. I think last week, not long ago. So if there's anything that's undocumented, you can refer to that white paper for more information. Again, I'm more an astronomer than a particle physicist. So I'll be introducing the snooze system, which is a network of neutrino detectors. But a lot of my talk is actually going to be focused around what we do after this network of neutrino facilities alerts us to the next galactic supernova. And that's where I'm so excited about how Grandma can help us with that. If this works, yeah, so this is just a countdown. A lot of the observations that I'm going to be describing are what we need to do in the first 24 hours following the supernova explosion alert from snooze. Okay, so why do I care? What are the big questions I'm trying to understand? What are the types of stars that explode? 40 plus years ago, it was thought that the generic supernova would be a red supergiant. But in fact, we find supernovae from stars at various evolutionary states. We've seen them as blue supergiants, yellow supergiants. And this is actually very important for us understanding the other question. How do stars explode? What is the mechanism that allows the core collapse process to proceed? When I started, I thought that I could understand this without understanding or having real appreciation, acknowledging what type of star it is. But in fact, to really understand the processes governing core collapse and the resulting EM signatures, multi-messenger actually, that we see, we need to know something about the progenitor star and its interior structure, because that can really change the final effects. And I'm not entirely sure of the crowd, but just to remind you of the importance of supernovae, why should we care? Well, supernovae are amongst the greatest cosmological influencers in the universe. So they contribute to the energy balance, structure, and chemical makeup of galaxies. They can trigger star formation. They're a significant source of dust. They produce a variety of exotic objects, including neutron stars, black holes, and some gamma ray bursts. They produce copious neutrinos, relevant for this talk, and they are progenitors of gravitational wave systems, the ones that Grandma follows up on, and they themselves produce gravitational waves. And of course, perhaps most important for us, we're here today because they manufacture heavy elements, and most of the heavy elements that make up the human body are from those produced in supernova explosions. So thus, it's terribly important to understand this fundamental process that goes on in the universe. I say often that as citizens of the universe, it's our responsibility to understand this. So how do we go about understanding core collapse explosion dynamics? Well, there's a lot of input physics that go into sophisticated simulation models that produce outputs. Okay. And these are observables that we can use to test the models and help constrain the input physics. A lot of my work is here. Okay. So we see many extragalactic supernovae, but they're unresolved. Okay. We can get light curves and we can take spectra of various epochs to understand general energies and yeah, energies and velocity evolutions, the chemical yields that they produce, some insight about explosion asymmetries and pulsar kicks. That's from supernova remnants, and I'll talk about that along with nucleosynthesis, and this explosion energies and remnant masses. At the end, I'll talk about this. This is the kind of understanding that you get out of a textbook. So a massive star, this being a star larger than about 8 or 10 solar masses, goes through successive stages of nuclear fusion, starting with hydrogen, helium, building up onion skin interior until it reaches iron core fusion. That is no longer exothermic. It robs the core of the radiative pressure needed to overcome gravity, and there's a subsequent collapse. Now, when the collapse reaches neutron degeneracy pressure, say this proto-neutron star says, I'm not going to collapse anymore under most scenarios, but not always, then there's a rebound shock. And it was thought that this first rebound shock would be enough to cause the supernova explosion. However, years of simulations, decades of simulations, failed to do this, which is to say they always collapse down further into a black hole. That prompt shock wave was not strong enough to overcome the infalling material, the ram pressure of the infalling material. So something else needed to contribute to the explosion. And right now I have my dog, Wilbur. I'm giving a talk right now. Sorry. Right now, the dominant mechanism is thought to be contribution from neutrinos. Okay? Neutrinos carry away the dominant energy of the explosion, 10 to the 53 ergs. And typically, neutrinos don't interact with matter. But at these intense densities and temperatures, some fraction of those neutrinos can interact and revive this standing shock and help push it forward. Okay. So I'm showing here 2 simulations of this process, so you have a visual. Let's go on the right here. This process of heating by the neutrinos is uneven, and this is in large part because there may be instabilities in the progenitor star structure where there's dense patches that get preferentially heated. This sets up this kind of sloshing back and forth. Can be called the standing accretion shock instability, SASI. You see this convective churning going back and forth. Over time, this builds up energy and the shock forward and explode the star. The other scenario, I'm focusing on neutrinos here, but the other scenario is if the core has a reasonable rotation that may set up magnetic fields, and that can aid in the explosion of the star. And extreme events like gamma ray bursts, that may be what actually drives this supernova explosion, have stronger energies than the uneven neutrino heating. Okay, and then finally, just a little, this is the last bit of background. This is where a lot of my work is. Okay. I use debris fields of supernovae, supernova remnants, and I do 3-dimensional reconstructions, both the kinematics, so how it's arranged, and the chemical abundances, the distribution. And it's kind of like a bomb squad investigation. I'm going into a room and I'm seeing how the material has been distributed, which tells us something about the explosion dynamics. And I could spend, a lot of time unpacking everything that's going on here. What I'm trying to show, the takeaway point, is that it's not random. Encoded in this distribution, right, which is coherent and has large scale structure, Here is a Mercator projection, so kind of like an Earth map of this supernova material. You can see that there are continents of ejecta, and they're not random. They have large-scale rings. Those rings we think are associated with overturning of nickel-rich material. So remember that simulation where I showed the neutrinos, there's hot spots of neutrinos, this uneven heating. Well, that may encourage this kind of overshooting, this mixing of nickel-rich material shown in blue, going out ahead of lighter elements. And here we have carbon in green, and red is oxygen. So this is a simulation. This is seconds and then hours after explosion. And this is centuries. Now, mind you, there's a lot that happens from here to there. But there's an interesting picture that seems to hold, which is to say, these nickel-rich plumes push out ahead of lighter elements, and through radioactive decay, it goes through nickel-56 to cobalt-56 to iron-56. The blue is tracing X-ray emitting iron, right? So the iron is tracing the original nickel distribution. And we see that in patches where there are large rings, and as this rotates around one more time, the largest ring has this very large deposit of iron. And it's consistent with this idea of the nickel moving out, expanding, pushing out, and compressing the lighter elements around it. And we see it as a ring because this is just the way that the remnant is being illuminated by a reverse shock. And the reverse shock is, think of it as a kind of a spherical shell, a shell that's highlighting only that distribution. And the cross section of a bubble that's being formed by the nickel-rich material originally, cross section is a ring. Okay, so I wanted to give a sense of the science. We're trying to understand how the explosion proceeded. And my science is trying to, particularly utilizes supernova remnants and their three-dimensional reconstructions to try and get back to what happened at the time of core collapse. Okay. But now, thanks to multi-messenger astronomy, there's a lot more opportunities to get information about the actual time of core collapse, because those neutrinos will stream out ahead and alert us. Here is the breakdown. So this is time relative to core bounds. Here's 0, and this is the time leading up to it. And this is energies. You can see the neutrino luminosity, much stronger than the other wavelengths. And you see that shock breakout. So what we see in EM wavelengths, UV, X-ray at the shock breakout particularly, and then later at optical, pales in comparison to the neutrinos. The problem being our sensitivity to neutrinos is not as good as in the EM band. So in a nutshell, the supernova early warning system tries to leverage the fact that the neutrinos for an explosion that happens in our own neighborhood, right? The neutrinos will provide the first alert that something is going on. Okay? There will be kind of a flooding of neutrino tank facilities, alerting us that a supernova is taking place. And the hope, the expectation, the desire is to act on that promptly and efficiently. I'll probably repeat that many times, to act on it promptly and efficiently. It will give us a heads up within minutes to hours. This depends on many things, in particular, just the radius of the star and how long it takes for that shock to propagate through it. So if it's a compact star, we don't have a lot of heads up time. But for the most likely scenario, which doesn't mean it's going to happen, but probabilistically, it's the most likely, it'll be a more extended star and we'll have several hours of lead time from when the alert happens to when the optical signature comes. Okay. By the way, a reminder for those who don't remember, multi-messenger astronomy started a long time ago. Okay. Here is a picture of Sanduliak -69202. And if there wasn't an arrow there, you wouldn't think much of this star because there's other stars. There's other star. I spoiled it. There's other stars of comparable brightness, and you see there's even a brighter region here. But of course, in February of 1987, this happened, Supernova 1987A. And I always make the joke, it's appropriate that was discovered by a Canadian. A, right? The first supernova, and A, because it's Canadian. There were approximately 20 neutrinos detected from supernova 1987A. And with present facilities, we have the opportunity to detect thousands of neutrinos from a galactic supernova. Here's 2 plots. This is from one of the detectors, and this is a plot showing all the detectors. And here you can see it as a function of time. Okay. So this was for 1987A. There's been significant improvement in detectability and in the number of facilities that are sensitive to neutrinos and to different flavors of neutrinos as well, providing an opportunity to get a spectrum to study. So here's a table taken from the white paper. So this is, yeah, these are numbers for a core collapse supernova at about 10 kiloparsecs. The 2 numbers here just depend on the mass hierarchy of the neutrinos. And then here they're showing what type of neutrinos that they're sensitive to. Most tend to be anti-electron neutrinos, but others have other sensitivity given the type of experiment that's being running and the type of material that's being used to be sensitive to it. So this is actually a place where those studying dark matter have an advantage in that they can be sensitive to any neutrinos, even though their numbers will be much smaller compared to others. So here is kind of what the signal is anticipated to look like. Here is time with respect to T bounce, that the moment that the collapse ensued, and then the prompt shock. We can see a strong portion here during the phase of deleptonization, and this is a strong signal that is kind of model independent. So all the facilities sensitive to these should be aware of this. And by the way, below, I've taken a figure from Griswold showing the expected detections for IceCube. Now, IceCube is designed to be sensitive to energies much higher. The energies of supernova neutrinos are about in the MeVs, 10 MeV. This is in the GeV band. But because they cover such a large space, they will notice a significant increase with respect to their background. And here you can see the background being displayed here. And then there's an increase in the signal. Okay. So one of the most important information is just when is T0? When did that actually collapse? When did the collapse happen? That is something facility to facility that can be shared. And that's what's happening in the network. So with the case being is, sure, if there's a nearby event, let's say Betelgeuse explodes at 200 parsecs, it's going to be obvious and clear. But what about something on the other side of the galaxy or even more distance? Maybe it collapses to a black hole and the signature is not as strong, right? There may be kind of lower threshold events that independent experiments may not have the significance enough to have confidence and say this is a bona fide event. But if you have multiple facilities that agree on it, then you feel confident in sending out an alert. Well, I won't go into detail, but there are various phases and there's anticipated neutrino signatures. There are some phases like this that is a little bit more model dependent, but this first phase around the actual core collapse is model independent. Here is the kind of schematic for the snooze server. Snooze, oh my gosh, typo already. So that's not a year. So snooze has been operational since 2005, but to date has never produced an alert. There's been no galactic supernova thus far. The upgrade to 2.0, and the upgrade has been supported by the National Science Foundation, which is why I showed the logo at the beginning, adds new facilities to it, and seeks to go beyond the original idea of, hey, something's happening, to, hey, something's happening, it's in some region of the sky, so there's a localization, and some minimal information about the nature of the event. And I'll go into more detail about that. Okay. Here is some description of the events. So each of these, if there's some event outside of normal operations, these get sent to the server that receives them. And if there's, it looks for multiple signals to be able to do some confidence testing on whether or not there's a bona fide event. Here's another map showing where the facilities are located around the globe. So Snooze 2.0 looks beyond just the time of core collapse, but has some kind of buffered time series to do a time sort, maybe fit some spectral templates to help align the time signatures. And there's the possibility to monitor for pre-supernova neutrinos. And that's for lower significance events that I was talking about. And then if there's a confidence, we send out an alert to various networks, and hopefully to the grandma network, which is why I'm here. And here's my window. I can see it. I can look here. Sarah, how am I for time? I see I'm at 20 minutes. Okay, so I should wrap up within the next 10 minutes, correct?
Yes. Yes.
Okay, please. Great. So what are the information? What information can snooze provide? One, as I said, something is happening. Okay. On some time scale afterwards, and we're taking the lead of the gravitational wave community here. So first, it's just an alert, hey, something's happening. And then as we further process the data, we can provide some kind of localization. That localization may be tens to hundreds of degrees. 10 years ago, that would have made an optical community laugh, like, oh, that's crazy wide field. But, that's, people don't flinch at that anymore. And then sometime later, with additional processing, some information about the nature of the explosion. So here I'm showing what I described here. Yeah, what I described earlier. So the localization may be from several to 100 square degrees. This depends on the number of facilities that are included in the triangulation and the strength of the signal, which of course is a function of how far away it is. You can see here 2 simulations of the localization field. Okay, here's an interesting thing. I always say that this is crazy, but it's possible. And that's the great challenge of reacting to a snooze alert. There's such a large parameter range. It could be next door. It could be faint and hardly detected. So we have to be prepared for a whole number of possible scenarios. In this case, those final stages of core burning can produce a neutrino signature that is, orders of magnitude less than the final core collapse. But if it's near enough, within about 1 kiloparsec, there's the opportunity to detect this pre-supernova lead up. Of course, everybody talks about Betelgeuse as a possible candidate. And so this is here where an example of where we can have we can leverage candidate systems. So if we detect pre-supernova neutrinos, we already have a good idea about which star it's likely to come at. So similar to when you're searching for follow-up in gravitational waves, you don't do the whole sky necessarily. You can look at possible galaxies. You constrain your search. This is the same thing that we would do. We would patrol these lists of nearby stars that are most likely to be supernova. But of course, that has to be also moderated with, something else may happen. So it's nice to have complementary, maybe shallower, wide field imaging that's encompassing the whole uncertainty region. Okay, this goes to attitudes, good and bad. And Sarah, this is why I liked your slide so much. It's exactly what I feel, is that this is the attitude that's terrible. And I encounter this all the time, that the next galactic supernova is so obvious, there's no need to plan a follow-up. People will just act on it. We want to avoid a free-for-all. And there is real rich scientific opportunities that will be lost unless there's a worldwide cooperative effort to coordinate the complex array of multi-messenger resources needed to fully characterize the next galactic supernova. Right? We want to minimize redundancy in observations. And if there are special purpose instruments that only certain facilities can provide, we want to be using those when other facilities can do complementary observations. This is a data set that should be for the whole world, because it's a once in a lifetime or longer opportunity. I'll just mention briefly that the gravitational wave follow-up will be guided by the snooze alert that will provide the timing information. So the gravitational wave signature for a core collapse supernova is not well constrained. There's a lot of uncertainty. In fact, I'll never forget when they called up Ray Weiss for the Nobel Prize, and they said, what's the most exciting thing you think that LIGO will be able to do? And he didn't say chasing after more black hole mergers or neutron star mergers. He said supernovae, because that's truly uncharted frontier. We don't know what the signature of a core collapse supernova is going to look like. So the timing information from the that kind of collapse and that peak that I showed earlier in the neutrino signal, that's a window into which the gravitational wave community can kind of zero in on where they should look for excess energy. Okay. Okay, so challenges and considerations for EM follow-up. Having some information of the nature of the event. So a supernova that produces a neutron star versus a black hole actually produces a different neutrino signature. In the black hole, there's an abrupt cutoff with the formation of the black hole. So there's an abrupt cutoff in the neutrino signal. So that helps inform a proper follow-up, right? If it's going to be a black hole explosion, it's going to be a supernova associated with black hole, it may be an implosion, it may be a very weak supernova. So that will inform the follow-up, right? We may change the observing strategy given the type of explosion it is. The distances, okay, dust. So that's, of course, something that we have to almost expect, is that the next galactic supernova will be on the other side of the galaxy, obscured heavily by dust. We have to push towards near-infrared longer wavelengths. And of course, location of the sky. If the galactic supernova happens during daytime, it's going to make follow-up in a lot of EM difficult. Radio will be okay, but a lot of other information will be more challenging. Characterization of the source. This is what I was talking about, that phase at which, if there's a black hole formation, there's an abrupt cutoff in the neutrino signature. Okay. I talked about this. I'm going to save everybody's time. It's very important to locate the star before shock breakout. We want to see what that star is doing before core collapse. That's because in extragalactic systems, there seems to be stars with precursor activity before the actual supernova. Now, see, supernova 2009 IP is a dumb name because there wasn't a supernova in 2009. There was just a luminous outburst. And this outburst was a precursor, part of precursor activity that preluded the actual supernova explosion. So it'd be great to be able to locate the star before the shock breakout to see what's happening to it before the supernova light overwhelms it. Okay. And there's various science and opportunities to be had with observing the actual shock breakout. Okay. To date, and I'll emphasize this and then I'll get to the end. To date, we have not been able to observe both the shock breakout and have precise timing of when core collapse occurred. Okay? We've observed shock breakout, but we don't know when the time of bounce is. And there's incredibly important information to be had about knowing how long it takes for that shock to propagate outward. That tells information about the interior structure of the star. Here's an example where they observed it serendipitously. I'll go back. This was a great story for an amateur. He just happened to have his telescope set up, imaging a sky because he got a new telescope. A new camera for his telescope, and he just happened to monitor the shock breakout of supernova 2016 GKG. 1 in 10 million chance, they say. There's Victor Busso there. Okay, that's going up. And then there's the follow-up, and this is something we can discuss more in the question and answer. What observations, once we've observed that shock breakout, what should we be doing afterwards? Given the full spectrum of electromagnetic radiation, what observations should we be prioritizing? We can look for mass loss interaction between the supernova and the blast wave as it sweeps over. Okay, and then last slide here, how to coordinate. This is where, so this is a slide taken from a previous talk, and I bring it here because I think what Grandma provides is the tools and the infrastructure and the communications needed to efficiently coordinate. I often say, even in the astronomers, we're recruiting from the human race, and there's this ridiculous competition amongst groups on who's going to get there first. Okay? My hope is to encourage, is to nurture this attitude that for a galactic supernova, we should all be participants in working together. And Grandma already has an alliance of nice, friendly people who want to focus on the science and set aside differences like this. So I was going to talk about refit, but I'm already over time. We can discuss that another time. I've already taken enough opportunity. You can see I was ambitious in what I wanted to talk with everybody today. So Sarah asked me for this slide, what does MMA bring to my research? As I emphasized before, multi-messenger astronomy opens up new ways to study core collapse supernovae. Neutrinos and gravitational waves offer direct and live views of the interior explosion. So gravitational waves are remember that simulation I showed, okay? They're sensitive to varied fluid instabilities, rotation, contribution rotation, structure of the protoneutron star that's being formed at the bottom, nuclear equation of state. And the neutrinos track that shock wave, the accretion phase onto the protoneutron star, cooling, possible formation of exotic matter, maybe quark stars, and that further collapse to a black hole. This is the information we get from neutrinos. And for me, this helps inform my research, because my research is looking to provide observable constraints for these simulations that are going to be making predictions about multi-messenger signals. And I'll leave my conclusions up front. I'm sorry, I'm a few minutes over time, and that's all. Thank you.